All right, let's do this. Time to get serious. We're gonna learn the little bit of calculus that we need for the early part of mechanics. This is on page 89 in this year's book, page 89. What we're gonna do is look at two cases. One of them is gonna be, we'll go back to math class land where we're just gonna work with some polynomial that's kind of meaningless polynomial and do some stuff to it. And then the second example, we'll actually put like a physics context to it, so you can kind of really see what you would use this kind of stuff for. What we're going to do is look at, like, okay, you're given this function y of x equals, and you're given this cubic thing, right? And what we need to do is you're given this crazy curve, and we need to find the slope of this thing. So as we've been talking about, your slope is what's called the derivative of that polynomial, and so we're going to find the slope. So the slope is going to be equal to. I'll introduce some notation that you're going to see in your calc class. They will sometimes call this y prime. Like if you start out with the function y, they might call it the slope y prime, or equivalently they might call it dy dx. It's the change in y as you change. It's the rise over the run, right? And so what we can do is take the derivative. So we'll use our little power lowering trick. Okay, so let's bring the 3 down, and I'll go nice and slow in the early going. So it's going to be 3 times what, 2x squared minus, let's bring that 2 down, 2 times 4x to the first. There's a 1 there, so you'd be like 1 times 3x to the 0. And then I wouldn't even bother with the constant, because there'd be like an x to the 0 if you want, and then bringing the 0 would kill it. The constant it's not changing, so there's no rate of change of that thing, so it doesn't contribute to the slope. And so now what we can do is simplify this, so you get 6x squared minus 8x, looks like plus 3. So you have this polynomial, right? The meaning of that polynomial, I could write either of these things. I'm just also going to just put the slope. What that is the slope anywhere you care to look, okay? And it turns out, for whatever reason, we care to look at x equals 2, so let's just check it. So let's plug in a 2. So 6 times 2 squared, 6 times 4, that's 24, minus 8 times 2 plus 3. 24 minus 16, that'll give you 8. 8 plus 3 is 11. So it turns out, lo and behold, the slope's 11 when you get to x equals 2. Let's actually see if that makes sense, because I graphed it on the next page. So at x equals 2, here's the function. Well, at least you can see that it's going to be a positive steep slope, okay? So apparently at x equals 2, this function out here, the slope is apparently 11, okay? Then what we're supposed to do is find the area between x equals 0 and x equals 1 of that function. And just so you can see where we're going with this, it's asking for this area. So we're going to find the area of this curvy little deal here. Right, so and you notice it's below the axis, so you can kind of anticipate that it's going to come out negative, but let's just sort of see what we get. So let's go back to that. Oh, I might have to erase that blob. Let's see. I'll just leave it, because then that'll remind us what we were looking at. So let's find the area between x equals 0, x equals 1. What we need to do here is find the antiderivative. This is a little bit awkward the way I wrote this. It's not really equal to it, but I'll show you kind of what I mean by that. Here, let me just draw like an arrow. So what we need to do is find the antiderivative. So notation that they'll use in calc is they'll tend to make it like a capital Y of x for like the accumulated area. And so let's do this. So we need to find a function that if we took its derivative, we would get this. So here's really how I think about it when I'm doing this, is the function that the antiderivative, the first term, it must just have an exponent that's higher, so like x to the 4th instead of x cubed. But if I take the derivative, I don't want 4x cubed, I want 2x cubed. So we can fix that by putting a 1/2 in the front. And now let's test it. 4 times 1/2 is 2. Score. So that's right. So now let's go to the next one. Next term's got to go like an x cubed. But I don't want 3x squared. I want a 4 here. So a common trick is you kind of put the thing you want to get rid of, which is the 3 in the bottom, and the thing you want, just put it on top. So by the time you bring the 3 down, you can see you'll get the -4. This must go like x squared, so plus some stuff times x squared. We want a 3 here instead of the 2 that we would get, so this must be 3 over 2. And then we get this will be -2x. Again, if you can see if you bring the 1 down, you'll get -2. And then there's going to be this arbitrary constant, right? And so what we need to do, so this function is the antiderivative, right? If you take the derivative of the constant, you get 0. So there can be any old arbitrary constant out there. To get the area between x equals 0 and x equals 1, what we need to do is actually evaluate the function at 1 minus the function at 0. Right? So let's do this. So if we evaluate the function at 1, that's going to be 1/2 minus 4/3 plus 3/2. That's why I chose 1, so this would be easy. Plus 3, oops, that's an ugly 3, sorry guys. 3/2 minus 2, and then plus c. All that junk is y at 1, and then minus y at 0, which is, well, 0. See, if you plug in 0, you get 0, 0, 0, 0, and then just the arbitrary constant. So you need to take the difference of these two things. You notice these will go away. C minus c. And then, what's this? 1/2 plus 3/2 is 4/2. So 4, which is 2. 2 minus 2, though, goes away. So these three things, the 1/2, the 3/2, that makes 2, minus 2. So the only thing, what you're left with is minus 4/3. So this says the accumulated, the area that you have of the function between x equals 0, which was here. If you remember this, the graph of the function, here was the axis, the axes, and here it was 0, and it went to here. So we're getting between 0 and 1, so we do get a negative area, okay? Which is okay, it was below the axis. If we wanted to get the area out to, say, 1.2, all we would have to do is change this 1 to a 1.2. If you wanted the area between 8 and 10, you would just do y at 10 minus, or capital Y at 10 minus capital Y at 8. So that's kind of how that works for just sort of an arbitrary function, and you're just doing slopes and areas. Let's put a physics context to this, though, so you can actually see how this would play out if something's moving. So one more little case with this. Let's do this. So this one says, suppose the velocity of something is given by this. So this is just telling you how fast it's moving as time goes by, right? Like apparently when the time started, it was going 20 maybe meters per second. So it says find the acceleration. Well, that's the rate of change of velocity, so it's going to be the slope. So the slope equals, that's going to be the derivative. Right, and the slope, by the way, is your acceleration function. So instead of just calling it the slope, it is going to be a of t. And let's take the derivative. So bring the 3 down. I'll go slow one more time. 3 times 3t squared. Right, I just brought the 3 down in front. So 3 times 3t squared. Minus 2 times 30t. And then this last term is just a constant, so it's not changing. So if you find its rate of change, it will be nothing, so it doesn't contribute. So you get 9t squared minus 60t, right? So you get this polynomial, and again, what the meaning of that polynomial is that is the acceleration at any time that you would happen to care about, at all. So, but we, as it turns out, care about t equals 1. You're like, I don't care about t equals 1. So what you do is just plug it in. So this is going to be 9 minus 60. So apparently the acceleration is minus 51, and it would be, if we were given units, it'd be like meter per second squared. So the slope of this graph is apparently negative 51 at t equals 1 second. We can check that maybe at the end of the video here. And then how far it's gone, right? Well, to find how far, you just, between t equals 0 and t equals 1, what you want to do, right, is calculate where is it at t equals 1 and where is it at t equals 0. So what we need is the position function, right? Well, to get the position from the velocity, it's the antiderivative, or the area, okay? So the area, we need to get the antiderivative. Okay, so x of t is going to be the antiderivative of this thing. So let's do what we did before. If this goes like t cubed, the antiderivative has got to go like t to the 4th. But we don't want, when we take that, we can double check now or go backwards. When we take the derivative, we would get 4t cubed, which isn't what we want. So we need to fix this by putting a 3/4 in the front. So now bring the 4 down, you get a 3 score. Then, let's see, minus something t cubed. Let's see, I don't want 3t squared, I want 30t squared. So that's going to give me a 10 in the front. Just check it out for a second. 30t squared, good again. And then plus 20t. You can check it. 1 times 20 gives you 20. And then plus an arbitrary constant. So now here's where you can start to get a physical reason, like, or it gives you a better feeling for why this arbitrary constant thing shows up. Notice what we were given to start with is, what this tells you, it just says, suppose the velocity of something is this. So this just tells you how fast and which way. It doesn't tell you anything whatsoever about where it is. So we knew nothing about where it started. But the thing is, the question just says, how far does it move between these two times? So it doesn't matter where it started. Who cares where it is? It just wants to know how far did you go between two times. So here's our position function. Well, so to find how far it went between those times, just see where did it end up and where did it start and take the difference between those two things, right? That's how far it moved, okay? I'm just gonna put this equals how far, okay? So let's check it out. So x at 1, again, I made it easy on us by just picking simple numbers like this. This is gonna be 3/4 minus 10 plus 20 plus the constant. That's x at 1, minus x at 0, which is 0, 0, 0, and then it gives you the c. So see, it doesn't matter where it started. It doesn't matter, because all we want to know is how far did it move from wherever the heck it was. So that kind of drops out. So let's see, so that goes away. Negative 10 plus 20 will give you 10, and then we have to add an additional 3/4. So apparently this thing moved 10.75. Well, if we were given units, I could say meters, but I guess we weren't really given the units. Right? So that lets you know kind of how far this thing moved in between those times. If you wanted to know how far it moved between t equals 8 and t equals 10, you would just do the same thing because you have the position function. Just check it at 10 and check it at 8 and find the difference. So that little skill of navigating between the position velocity and acceleration functions will actually get you pretty far in mechanics. So not too bad. You just got to know how to do the power lowering and sort of power raising to go backwards.